Hello students, welcome back to Math 332 Elementary Linear Algebra. We are at the very end of the semester, so yeah, right. Okay, in this video we are going to look at the so-called least square method. And this is also a very interesting video where you can see how the previous concept that we learned can be put together to solve problems that you have seen before actually if you have done experiments for your science courses. You know that sometimes the theory predicts that something should be fall into a straight line, but your observations give you data that would not fall into a straight line. That's obviously because of observational error, measurement error, and all that. So we want to find a line that best fits the data in the sense that it will minimize the error. So we'll talk about precisely what minimizing error means in this context, and what errors and minimizing error, and how do we able to find best fits equations using the concept of projections, using the concept of orthogonal complements. When we first talk about this, these are pretty abstract idea, right? We talk about orthogonal complement of a vector space. Strange, like why do we want to talk about orthogonal complement of a vector space? Why do we care about the fundamental theorem of linear algebra? Why we care about the relationship between a column space and the null space of A transpose and all that? And you can see we managed to put all of that together in these videos. It's going to be a little bit computational, but mostly conceptual. But I'm not going to talk about the main proof here in the theorem because we work on that before in homework and in class meeting. So we will try to put that aside. Try to just put the proof, the main proof of the theorem aside, give you all the motivations to convince you that it has to be like that, without showing you all the detail of that particular proof. But it's in the notes, and you can look up. You can look it up. It's not difficult, and we already did a lot of preparatory works so that you'll be able to understand that. Okay. So without further delay, let's get right to it. All right. So let's look at the objective for the method of least square. So the objectives are pretty straightforward. You need to know how to find a best fits equations using the least square methods, and basically understand how it works through orthogonal projection. So we have developed a lot of theory before this on orthogonal projections and all that, and we are going to put all of that in this videos in order to show you how we can actually apply them and develop the so-called least square methods. All right, so what is the least square methods? Now, let me motivate the problem here with an example. All right, so in this example, we are looking for a line, straight line, that best fits this set of data. We will explain what best fits means, okay, later on. But right now, we are given this data. This is our x coordinate, this is our y coordinates. And so we're looking for a straight line, okay, such that if you substitute all this x and y into these equations to generate these three equations, these are basically substituting our y equal to 2, x equal to 1, y equal to 2, x equal to 2, y equal to 4, and x equal to 3. These are coming from this data. And want to find, can we find a and b? So a and b is what we want to find, right? So we want to find a and b that will give us a best line, best fits line, in the sense that it minimizes error. So we will talk about exactly what's our error here means in a minute. But right now, it's pretty straightforward. We have y equal to a plus bx, and we substitute all this data into these equations, and we want to find a line. You see that? We want to find a line. In this case, you can see that in this picture here, the line doesn't even have to pass through any one of those points. We just want to find a line that's minimize error. So we'll talk about what minimize error means. And obviously, if all these 3 points are really on the line, then we can actually find an equation of the line that these 3 points will stay on the line. But in a lot of cases, as you know, when you do experiments in science and all that, because of error and this and that, even though your theory suggests that it should be, all the data points should be on a straight line, you know that it's rarely that you're going to hit all the points on a straight line. So because of experimental error and practical purposes, there are experimental error and all that will make you have data point that is not on the line, even though theoretically they should be on a straight line. Okay, so let's look at this system of equation in AB, all right, not in XY anymore, because XY is gone. We substitute the X and Y with all this data point, okay? So look at this equation in AB. So what do we want to do? We want to find AB, right? So we want to find A and B. And you realize that, okay, this is exactly the same as this equation, and you can put it in the matrix form like this. And the problem is, this system is inconsistent because, as I said, most of the time, even if you know theoretically, all your data points should be on a straight line, but most of the time, when you take your data because of error and stuff, they are not on a straight line. And in this case, you can actually check that this system is inconsistent. There's no A and B that will make all the points on this line. There are no A and B. There's no way you can find any A and B such that all the data point fall into this line right here. Okay, so we call that this system is inconsistent. Okay, you can check that very easily. And what we want to do, as we spell out right here, is to find a line that come close, okay, that come as close as possible to those data points. Okay, all right, so for any line, we'll measure the vertical distance on each data point. And as I said right here, you can see in the picture right here, this vertical distance, okay, this vertical distance, right? We want this vertical distance, okay, right? This vertical distance here basically represent errors, right? So the error from the actual values that we predicted with the actual data that we actually computed. So we can actually denote all this vertical distance by epsilon 1, epsilon 2, and epsilon 3, and we can form the error vectors. We collect all this vertical distance. This is going to be like our epsilon 1, epsilon 2, and epsilon 3. Okay, we are collecting all the so-called error, and we want this error to be as small as possible in this sense. So we put all this thing in a column vectors. So the length of that column vectors is given by this. Okay, and what we want to do in this case, when we say we want to find a best fit line, is we want to minimize this particular error right here. And again, just like in calculus, we know that we hate to work with square root because square root is annoying. So this is the same, if you want to minimize this, it is the same as minimizing this, okay? If you can make this small, you will make this small. If you can make this small, you can make this small. They're equivalent, okay? So that's the reason why we have the so-called least square method. So what we want to do is to find AB so that the error is all been minimized. What is error? Error all this vertical distance. So we want the sum. We want this particular quantity. Okay. All right. We want this particular quantity here to be as small as possible. All right. Before we proceed any further, I want you to spend time to really, really understand what is going on here in these pictures, okay? So we have this line, y equal to a plus bx, right? And let's concentrate on this data point 1, 2. These are the data point that you collected, x equal to 1 and y equals to 2. So suppose we have this line, okay, y equal to a plus bx. The y coordinates for this equation right here will be given by a plus b and substitute x equal to 1 here. This should be pretty straightforward, okay? So both of them here have x coordinate 1, obviously, and the y coordinates, the data point that you collected is 2, and the y coordinates that is on this line is this. That should be clear. And so as I mentioned earlier, the vertical distance is what we want to look at, right? So the vertical distance here is what we call error 1, that's epsilon 1 right here. So this is measured from the y-axis. This is the vertical distance, okay? So as you can see from this picture here, how big is this line, right? How long is this line? What is the distance between these 2 points? Obviously, the distance between these 2 points is 2 minus away this quantity right here. As you can see, epsilon 1, okay? Epsilon 1 here is 2 minus away this quantity right here. So this quantity right here are the values, that is the y values that is on that particular y equal to a plus bx line. Now, if you do that for all the 3 points, you get epsilon 1, epsilon 2, epsilon 3. Remember, these are the quantity that we want to minimize. But if you look at the epsilon 1, 2, and 3, they are this, okay? All right. Now, I want you to see that actually, if you put this as our column vectors, just right here, right? You will see that this equations right here is actually given by B, all right, 2, 2, 4, 2, 2, 4, we call that vector B, minus this matrix A and this matrix X here, which we call A and B. The things that we want to find is X, right? That's what we usually do. So the quantity that we want to find is X. You've been brainwashed since you're in preschool that the things that you want to find is called X. Or we call it X, right? So this is why we want to find A, B. And you will see that the error is actually coming from B minus AX. So this is our error. This is our error here, okay? So our column vectors, this thing right here, another way of seeing it is to see it as B minus AX. So our error vectors, okay, our error vectors is now B minus AX. Now, this is also very intuitive in the sense that if our error vector is 0, which means there's no error whatsoever, then you will have AX equals to B, right? So if you have AX equals to B, then there's no error. Everything will fit, right? The system was consistent, AX equal to B. But if your system is not consistent, if you take this difference, the difference between B minus AX, which translates into this vertical distance here, this are the error vectors where each quantity here coincides with this vertical distance from the graph, okay? So if we have the error vectors as non-zero, then B minus AX is actually inconsistent. You can't really find a line that passes through all that 3 points, okay? All right, so now we have our questions. Our question is very, very simple. Our questions is also something that you have seen long time before linear algebra. So you definitely have taken some science classes where you have to do some experiments and you have some data point and you want to try to find a straight line. And last time you kind of like eyeball it to find a line that's just kind of like have a lot of data point that's on the top of the line and some of it below the line so that you kind of balance out, right? You kind of eyeball it. So we have a questions like this, okay, right? Which we want to find the A, B, and we want it to be very precise. So we say that, hey, this is so-called our error vectors, and our objective is to minimize this, okay? So minimize this, and it turns out our error vectors is B minus AX, and our error vector is non-zero, then your system is inconsistent, okay? So this is the setup. This is the setup. Now, how is all this have anything to do with linear algebra? Well, okay, wow, glad that you asked. Okay, so now, look, we have a linear system, AX equals to B. We know that the system is inconsistent. What does it mean in terms of B and the column space of A, right? So what is, by this time you should know already, if this system is inconsistent, what can you say about the vector B and the column space of A? And you know, obviously, that B is not a member of the column space of A. We have a criteria, right? We have a criteria. We know everything about the consistency of the system. The system is consistent if and only if this vector B is in the column space of A. Now, okay, so now we have that the system is inconsistent. So your B is actually not in the column space of A. Now, just for simplicity, okay, for simplicity, I am going to draw, this is just a cartoon, okay? This is just a conceptual diagram. It doesn't really have to look like this. So let's say our column space of A looks like this, okay? It's a vector space, and it's a plane, actually. So it should actually go, you know, like, it's difficult to draw the whole thing. So let's just imagine that it's like a plane like this, okay? So this is column space of A. So if I ask you to draw B, knowing that this system is inconsistent, so if this system is inconsistent, your B cannot be on column space of A. If your B is on the column space of A, then the system is actually consistent. So the linear system is inconsistent, giving that this system is inconsistent, meaning that your B here will not be on the column space of A. All right, so now, okay, so the problem is, okay, so now this is not on the column space of A. So what happened is I wanted to find, okay, so, okay, this projection's right here. We can find a projection onto a subspace. That is something that we know how to do from before. All All right, so this is something that we know how to do from before. So let's imagine that we shine a light right on top of it. So it will cast a shadow. Now this shadow right here gives us a vector. The shadow right here gives us a vector. This is known as the projections of B onto our column space of A. All right, so this is our projection of B onto our column space of A. Now, we know, okay, that if you reverse this position, this is all the things that we know from before, nothing really new, okay? So we know that if you reverse the positions and you look at B plus the minus of the projections of B on the column space of A, which will give us this, right? So this vector right here, this vector right here is B, right, minus the projections of B onto the column space of A, right? What do we know? We know that this quantity right here is definitely orthogonal to every element in the column space of A. So this is what we say that B minus the projection of B onto column space of A is a member of the column space of A perp. This is everything that we know, okay? Right, that's everything that we know. All right, so let me, okay, let me, for simplicity, let me say that, let me denote, okay, so that's notations, notation is notations. Let me denote the projections of B onto the column space of A as AX hat, right? This is called X hat, right? Okay, if you've physics major, you do that all the time. Okay, well, anyway, so why do we say it like this? Why do I say the projection of B onto column space of A? Let's denote it as AX hat. Well, first of all, the projections of B onto column space of A, this is on the column space of A. That's what you do. You project it onto the column space of A. So whatever this quantity is, I definitely can find some vectors so that A of X will equal to this, because this is, right, B is not in the column space of A, but this projection is. So this projection is. So we know that the system AX equals to the projections, right? AX equals to the projections of B onto the column space of A is consistent, right? Because this is on the column space of A, right? So this system is consistent. We call the solutions AX hat. All right, so I denote that, right? So I don't want to call projection of B onto column space of A so many times. I'm just going to call it AX hat, okay? So this is now denoted as AX hat. There's a reason behind all this notation, though. I'm just explaining that to you. So this is called AX hat, all right? So obviously right here, let me write bigger, AX hat. So this will be B minus AX hat. This will be B minus AX hat. All right, okay? Okay, so this is good. So far, so good. All right, now, this is B minus AX hat. This is the vector, which is right here. But you know that we can actually move them here. You know, like this, all these vectors are equivalents. You can freely move them as long as they are still pointing to the same directions and have the same magnitudes. Okay, so now we have that. Now, obviously, these are all vectors, so we can also find the magnitude of the vectors. So the magnitude of the vector is what? It's the length, right? So it's a length in this diagram. This will be the length, okay? That will be the magnitude of that vector, and so on and so forth, okay? So far, so good. Now, okay, so we suppose, right? So suppose you take an element, you take a quantity, let's say x1, okay, right? Let's call it AP. Let's call it AP, okay? So AP, right, is in the column space of A, obviously, right? Right, so if we want to draw AP, we'll have to draw AP right here. So this is our AP. All right, why is it AP is in the column space of A? This is obvious. This is basically almost like by definition. We should know that, right? So AP is definitely in the column space of A. So let's draw them like that. This is AP. Now let's look at another quantity. Let's look at another quantity, which is B, right? So let's look at AP, right, which is here. And then let's look at this vector right here. Let's look at this vector right here. This vector right here. So this is simple vectors diagram. If this is AP, if this is AP, right, this is another vectors, right? This one's is unknown vectors. So AP plus these unknown vectors give you B, right? AP plus these unknown vectors give you B. So what is that unknown vectors? That unknown vector is B minus AP, right? So we can label that. This unknown vectors right here, okay, is B minus AP. All right, so far so good. So this is just labeling. This is our B minus AP. AP is in the column space of A, obviously, and B minus AP is that vectors. Now, from this diagram, you can kind of convince yourself that, from this diagram, you can kind of see that, all right, comparing these two distance, which distance are we talking about? This distance right here. Compare this distance right here and this distance right here. Which one do you think is shorter? Which one do you think is shorter? This in terms of length is shorter, or this in terms of length is shorter? Well, the answer should be clear, right? Orthogonal projection. So intuitively, this is like 90 degrees, right? So if you look at this diagram, this triangle here, right? You look at this triangle here, right? So this triangle that we're drawing, this is the hypotenuse of this right angle triangle. So, I mean, just by inspecting also, you can kind of see that this B minus AB in terms of length, right? B minus AB in terms of length, B minus AP in terms of length, this is definitely greater than the length right here, this length right here, which is B minus AX hat, okay? Right, so B minus AP seems to be always greater than B minus AX hat from the way we draw them and so on and so forth. So B minus AX hat, right, is the smallest, okay, so to speak. Okay, B minus AP will be bigger. Now, the P here, I just randomly pick one, right? So the AP here is just it's just like arbitrarily fixed element that is in the column space of A. So this should hold true. Okay, so this should hold true for all the elements that is in the column space of A. We always have that, right? AP here is just a representation. We can draw AP differently. We can draw AP differently, right? We can draw, okay, my AP is right here. This is my AP. So this is a distance. So this distance here compared to the distance, obviously this is bigger. You can try draw a few pictures to see it. That if your AP, okay, and elements in the column space of A, then B minus AP in terms of magnitude, is going to be greater than this thing right here. B minus AX hat. All right, AX hat right here is a projection. So this is B minus a projection. Okay, so you know that we can prove anything using a pictures. So we actually provide a rigorous proof of the fact. Okay, we actually provide a rigorous proof of the fact in the notes right here. You can take a look right here. All right, so now let's look at page 3 of our notes, okay, to go over the things that I just mentioned. All right, so now if you pick any x, okay, all right, and our generic setting here, okay, our A is m by n, right? So you have A, right? So a generic setting, okay? So our AX here, this is m by n, so this is n by 1. So I'm saying that if you pick any x that is from Rn, AX, okay, this quantity is definitely a member in the column space of A. All right, so if we draw it, just like I mentioned earlier, you can draw AX like this. Just now I draw AP, right? Now I draw AX, I can draw AQ. They are all in column space of A, right? Because things that looks like this is definitely in the column space of A. So I draw that, okay? Previously, I pick a P that is in Rn. So I look at AP, so I have like AP that is like this on the column space of A, that's fine. I can pick a Q that is in Rn. So I can pick a Q that is in Rn, right? So AQ will be maybe somewhere here, doesn't really matter, AQ, but the key thing is they're all on the column space of A, all right? Okay, now, so if you pick any generic X that is from Rn and look at this elements right here, this is in the column space of A, so I draw it right here, okay? And if you look at this vectors, which is B minus AX, right? And if you look at this magnitude, if you look at the length, and you will see that this length here is greater or equals to this length right here. This length right here is this length, b minus ax hat. Okay, there's a typo here. It's b minus ax hat. Okay, now why is it so? Well, look at this. This is kind of like, if this is 90 degrees, this is the hypotenuse of this triangle right here. Right, obviously this is bigger than this one. Right, we can prove that. We can prove that. I assure you this is true. Not by drawing picture, we can prove it. We can prove it. This is math. We will prove stuff. Now, before we do anything, all right. So let's just be very clear. What we have seen, and we will show you the proof in a minute in these notes actually, that this quantity right here is the smallest among all the b minus ax. Okay, now this is a varying quantity. You pick any x that is in Rn, then you can compute this and you compare to this. This one right here, remember what x hat is. This is a fixed quantity, nothing changed here. We know what b is. Okay, this is given. We know x hat is the projection. Ax hat is the projections of our b onto our column space of A. So this is again a fixed quantity. Nothing changed, okay? Nothing changed. These are fixed quantity, okay? B is fixed. B is fixed, right? B is given. B is fixed. Ax hat is fixed. So these are fixed quantity. Think of it as a fixed number. This is a fixed number, right? However, your right-hand side is not fixed. Your right-hand side is something that you are free to choose. You can choose x, you can compute this, and it turns out this is bigger than or equals to this b minus ax hat. If you change to p, right, and compute this, again, this is going to be bigger. If you change to q, if you compute this, this is again still going to be bigger. If you change to y and you compute this, this is still going to be bigger. So this is the quantity that is keep changing. But no matter how you change it, this seems to be the smallest one. All right, this seems to be the smallest numbers among all the possible b minus ax, right? Among all the possible b minus ax, which means that no matter how you draw it, right, this length here is always bigger or equals to this length. Okay, now, so what all this is about? Well, this is error, right? This is what we mentioned earlier. This is our error. So have we found our minimum error? Yes, we found our minimum error. This is our minimum error. This is our minimum error. Okay, so what do we want to do now? Well, we want to find what we want to find. So we want to find x hat, because we know that if we found x hat, right, once we found x hat, okay, x hat, right, will give us the best fit solution, because the ax hat is right here, right? Yeah, right. So you cannot solve ax equal to b, but you can solve for the x hat, which is in this picture. Why we solve for the x hat in the picture? Because b minus ax hat here will give us the smallest possible error. So that's the very important conceptual pictures. And as you can see, it involves our column space and it involves our projections, our projection vectors. Okay? Okay, now, you might want to say that, hey, okay, show me the proof of this. Show me the proof of this. How do you know this is true? Show me the proof of this. Not drawing a picture. Drawing a picture is not a proof. Well, don't worry about it. We will talk about it in class and exercises and in homework and all that. But this is given this theorem right here. I'm pretty sure that we'll spend a lot of time working in class. That I mean, I'll give you all the necessary tools and guidance for you to understand all this. But it's not very difficult. Not very difficult at all. In fact, you can see the proof is pretty straightforward. Look at the proof. It's only like this. It did something clever. Something clever here is to write b minus w as this, and the rest follow pretty easily using the property of projections and w perp, and we got that. Okay, all right. I guarantee you this is proven. This is true. Okay, we have those results. Okay, we have those results. So I just want to conclude here by saying that, hey, we want to find x hat, right? So that ax hat is our projections of b onto our column space of it. This, okay, is good. We want x hat, all right? We want x hat because x hat's right here, okay, right? x hat right here will make our ax hat b minus ax hat. Right, b minus ax hat right here, okay, to be our minimum error, okay, to be our minimum error, least error, okay. So we want to find x hat. All right, okay, we have that, right? So now ax hat is actually projections of b onto the column space of A, and we want to find x hat. Now you know, we know how to find projections of B on the column space of A. We actually know how to do this. It's tedious, first of all, from the previous videos. You know that if we actually have to compute this, okay, using our previous methods, we actually have to find an orthogonal basis. We have to find orthogonal basis for our column space of A, right? And then we will have to compute the dot products and something plus dot product, something, right? Some vectors plus dot product. You know, I mean, if we are given we can find orthogonal basis for a column space of A, and this is all computable. It's not very difficult. However, we don't actually need to do that, okay? This is another fun part. The fun part is the fundamental theorem of linear algebra can actually help us avoid computing this projection vectors by actually computing a projection vector. We can actually do something cooler than that without actually doing anything involving dot products, okay? So what happened here, right? So what happened here? Now, okay, so this is key. So now, all right, so we wanted to compute this x hat, okay, ax hat, well, without actually computing our projections, okay? All right, the thing we do is to look at this quantity, b minus ax hat. All right, okay. So this is b minus our projections of b onto the column space of A. I'm not doing anything. I'm just writing something that's trivial. I have ax hats equal to this, so now I look at b minus ax hats. Now, why do we want to do that? Well, you'll see soon. Now, let's call this equation star, okay? This is our equation star. Let's now multiply this equations on both sides by A transpose, okay? So multiply A transpose here, multiply A transpose here, all right? Now, why do I want to do that? Well, if you notice that this B minus the projections of B onto the column space of A, right, is actually a member in the column space of A perp. See this, right? See this every time when you have a projection, right? So this quantity right here, right? You have a B, you have B minus the projections of B onto the column space of A, right? So this is our B minus our projections. Our B minus our projection is always a member of this space perp, right? This is written right here. B minus our projection of B onto the column space of A is actually a member of the column space of A perp. But fundamental theorem of linear algebra says that CA perp is the null space of A transpose. All right, CA perp is the null space of A transpose. What does that imply? All right, that implies, okay, that this quantity right here, B minus the projection of B onto the column space A, is a member of the null space of A transpose. So if you multiply this vector with A transpose, this gives us a zero vectors. That's what it means for being in a null space of the matrix, right? If you are in a null space of this matrix, right, then if you are in the null space of this matrix, then B of x equals to 0. That's what null space means. That's what null space means. All right. So now, okay, we have this one in CA perp, and CA perp is a null space of A transpose. So we have this thing equal to 0. All right. So if you, okay, get rid of all this detail and just write this thing here as 0, then it gives us a very simple equation to find the x hat, okay? To find the x hat, we don't have to do any projection anymore. It seems like to find the x hat, we just have to solve this equation, distribute. That's what this equation means. And in order to find the x hat, turns out we only need to solve this equations, which is known as the normal equation. Take A transpose multiply A, x hat equals to A transpose B. So the x hat is found by solving this so-called normal equations. All right? Okay, so you just have to solve this so-called normal equations. right? To find the x hat, I actually doesn't have to do any projection computations using orthogonal basis and all that. We don't need to anymore because we can just simply solve this equation. And in fact, if your columns are all independent, these vectors is A transpose T will be invertible, and you can also find x hat by invert this across. So it's up to your preference. Okay, you can either solve the normal equations using RREF methods, or you can solve this cis x right here by finding the inverse of this matrix. Okay, let's show you one example. Let's show you very quickly. Remember on our example originally? So our example is this one, right? We want to find our AB so that it will give us the least error. So if you compute A, this is our matrix A transpose A give you this matrix. A transpose B is computational, give you this matrix. So this system right here can be already after this. So x hat is our 2 over 3 and 1. X hat right here is 2 over 3 and 1. And if you take this as our AB, the best AB that minimize error. So we realize that's 2 over 3 and 1. Okay, y equals to 2 over 3 plus b, which is 1x. This is the line that will give us the least square solutions. This is the line right here. If you look at the very beginning, this is the line that will give us the least square solutions. Pretty neat. There are two things that you have to know. The projection have the special property, and to find x hats, we use a fundamental theorem of linear algebra, and computationally, it's just pretty neat to do that, right? So if I ask you to apply the least square methods, okay, without understanding what's going on, if you're just following the formula, you just compute this, all right? But you can see that we have that formula precisely because of our understanding on the projections and our standings on the orthogonal spaces, and it's pretty neat, right? So this is one of the things that you can do also by inverting, and that is basically what we want to show you. All right, let me give you another example. This is the last example, a computational example. All right, so again, if you first look at this, you will be like, wait a minute, this is not linear equation. Well, we are try to find an equation of this form that best fit this data point. So these are our data point. These are our xy coordinate, okay? So when you substitute into our equation here, you will see that we have the linear equation in AB, right? Not in xy, but in AB. So what we want to find? We want to find our AB. We want to find our AB so that this, okay, will best fit this data points, okay? So what we do, well, look, rewrite this system as AX equals to B, right? Okay, and what do we want to do? We want to find X hat. X hat is the one that will give us the least error solutions, okay? This is going to give us the least error solutions, and you can look at the computations. This is going to be our best fit solutions, all right? Right, this is computation is pretty straightforward. The only things, I mean, you have to go through it yourself. It's not difficult to do it. The only thing you have to know is that, wait, why do we have that formulas? Why do we have that formulas? Why do we have that formulas? Everything is just hinges on page 3. Everything is just hinges on these pictures right here. Okay, all right, the projections. Remember, you shine a light right on top of B. This is our projections. Is our projections of B onto the column space of A. All right, so this, okay, right, okay, once you have this distance right here, which corresponds to error, this distance right here, okay, this fixed distance right here, okay, remember, your B is fixed, right? So if you project your B onto the column space of A, shine a light, right? Remember, shine a light on this, it casts a shadow here. This shadow here is fixed, it's not changing. This shadow here is fixed, it's not changing. Okay, so you cast you shine a light right on top of this vector B, it's cast a shadow on the column space of A, right? So this is a fixed quantity. So this is also a fixed quantity, therefore this is also a fixed quantity. And if you take any vectors that's in the column space of A, you look at this so-called error, this so-called error is going to be greater or equal to this one. So this is our least square solutions. And to find this, we actually use this property of projections and orthogonal subspaces. And turns out, if you want to find the x hat to have a least square solutions, the best fit solutions, you can find it by solving this normal system. This is called normal equations. Or if your column space of the vector A matrix A is independence, you can actually also invert this across. You get this result. Okay, and that's it. Pretty neat. All right, so that's conclude our discussions on these particular sections, and I will see you in another video soon. Bye.